On a previous video how to connect solar panels in series or in parallel, along with the advantages and disadvantages of these two connection methods. However, all these explanations were based on identical panels. In practice, you may often find yourself connecting solar panels with different characteristics, whether it's voltage, current, power, or even the brand. Connecting different panels together is not without consequences. So today, we'll examine various examples to understand how to connect them properly to minimize performance losses and wiring errors. But before we begin, don't forget to subscribe to the channel, give it a thumbs up, and feel free to ask your questions in the comments. Before diving into examples of connecting panels with different characteristics, let's first review the basics of a series connection with two panels, each with a power of 305 watts, a voltage of 32.5 volts, and a current of 9.38 amps. Quick reminder, using the formula P equals V times I, 32.5 volts multiplied by 9.38 amps indeed equals approximately 305 watts. In a series connection, the voltages add up, while the current in amperes remains constant regardless of the number of panels in the series. In this specific case, we will therefore have a voltage of 65 volts and a current of approximately 9.38 amps. The power, in turn, will be 610 watts. For a parallel setup with the same panels, still with 305 watts of power, it's the currents that add up, while the voltage remains constant. So, in this configuration, we would have an overall voltage of 32.5 volts and a current of approximately 18.8 amps. The power would also be 610 watts. I'd like to take this opportunity to point out that for parallel connections, you can use connectors of this type, double or up to 4 connectors, but you must of course check the maximum current, which is sometimes limited to 30 amps depending on the connectors. In my previous video, some viewers pointed this out when I had only shown an image to illustrate my explanation, but it turned out to be a very relevant observation. I want to thank those who comment on my videos, by the way. The safest option, however, is to use bus bars. With these, the current can easily go up to 250 amps without any issues. We also covered the mixed series parallel configuration. For this example, we'll use 4 panels to make it clearer. Here, we'll have 2 pairs of panels connected in series, and then these 2 sets will be connected in parallel. Let's stick with the same panels as before. In this setup, we'll have 32.5 volts plus 32.5 volts, resulting in 65 volts with a current of 9.38 amps and a power of 610 watts for each series connected pair. The same will apply to the second set, as we are still using identical panels. Now, when we connect these 2 sets in parallel, the voltage will remain unchanged at 65 volts, while the current will increase from 9.38 amps to 18.8 amps. This will give us a total power of 4 times 305 watts or 1220 watts. You can use connectors here since the current is still relatively low, or you can opt for bus bars. Once again, if you'd like to better understand the advantages and disadvantages of series versus parallel connections, I encourage you to check out my previous video on the channel. Now let's see what happens when we connect 2 panels of different brands and characteristics and the resulting consequences. We'll calculate the total power generated for each configuration, series and parallel. Characteristics of the 2 panels: Victron Energy Blue Solar, 305 watts, 32.5 volts, 9.38 amps. Renogy, 175 watts, 18.1 volts, 9.67A. The theoretical total power of these 2 panels is 480 watts, but that's just in theory. Let's start our calculation with a parallel connection this time. In a parallel connection, the currents add up and the voltage is limited to the lowest of the 2. Here, this gives us a voltage of 18.1 volts. Since the currents add up, 9.67 amps plus 9.38 amps equals 19.05 amps. The total power is therefore calculated by multiplying 18.1 by 19.05, which gives us 344.8 watts. The efficiency compared to the theoretical total power will therefore be only 71.83%. That's quite a significant loss, so let's see how it looks with the series configuration. In a series connection, the voltages add up, and the current is limited to the lowest of the 2. Here, this gives us a voltage of 32.5 volts plus 18.1 volts equals 50.6 volts. Since the currents are quite close, 9.38 amps and 9.67 amps, we must use the lowest value, which is 9.38 amps. With these values, the total power is calculated as 50.6 volts multiplied by 9.38 amps, which gives us 474.6 watts. In this case, the efficiency compared to the theoretical total power is much better, as it reaches 98.87%. Here is a table to compare the 2 setups. Even though these are two different panels, their operating currents were very close, so the series connection resulted in minimal loss. In parallel, the difference in voltage severely limits the overall efficiency. Let's now move on to a much more interesting setup for your understanding, which I hope will make you an expert on series parallel wiring, this time with 3 panels of different specifications. Panel specifications. Panel 1, 305 watts, 32.5 volts, 9.38 amps. Panel 2, 175 watts, 18.1 volts, 9.67. Panel 3, 100 watts, 20.4 volts, 4.91 amps. In reality, I added a 100 watt Renogy panel, and you'll see that this significantly changes the results. The total theoretical power of this system is 580 watts. We'll start by wiring these 3 panels in series. As a reminder, in a series connection, the voltages add up, and the current in amperes will be limited by the panel with the lowest current. So this gives us a total voltage of 32.5 plus 18.1 plus 20.4 equals 71 volts. The total current will be limited to the lowest current value, which is 4.91 amps. The total power is therefore calculated by multiplying 71 volts by 4.91 amps, which gives us 348.6 watts, while the theoretical power is 580 watts. That's really not great, is it? The efficiency will therefore be only 60.1%. This is a very inefficient configuration that we cannot consider. Now let's calculate with a parallel connection of these 3 solar panels. As we've already mentioned, in a parallel connection, the currents add up, and the voltage is limited to the panel with the lowest voltage. The total voltage will therefore be 18.1 volts, which is the lowest voltage among the 3 panels. The total current is calculated by adding 9.38 amps plus 9.67 amps plus 4.91 amps equals 23.96 amps. With these values, the total power will be 433.6 watts. This corresponds to an efficiency of 74.8%. While this configuration is certainly more efficient than the series connection, it's still far from ideal, wouldn't you agree? Third option to try to improve this setup. Divide the system into 2 groups with the following scenario: panels 2 and 3 in series, plus panel 1 alone. Let's see what this gives us. Group 1 in series. Panels 2 plus 3. The voltage will be 18.1 volts plus 20.4 volts equals 38.5 volts. The current will be 4.91 amps. Group 2 panel 1 alone voltage 32.5 volts current, 9.38A. Then, these 2 groups are connected in parallel. The total voltage will be the lower voltage, which is 32.5 volts. The total current will be 4.91A plus 9.38A equals 14.29A. This gives us a calculated power of 32.5 volts times 14.29 amps equals 464.4 watts. Here, we improve efficiency to 80.1%. This remains the most optimal configuration without adding any devices, but for me, it is still insufficient in this particular case. For this type of scenario, using 2 separate MPPT controllers is often the best solution when dealing with panels that have very different specifications. Here's a better configuration, again with 2 groups, an MPPT controller connected to panels 1 and 2 in series. This gives us a total voltage of 50.6 volts, a current of 9.38 amps, and a total power of 474.6 watts, which corresponds to an efficiency of 98.87%, virtually no loss. An MPPT controller connected exclusively to panel 3. Here it will deliver its 100 watts, no loss, thus optimal efficiency. In this table, you can see a summary of all the connection variants we've tried and the most efficient one. Advantages of this configuration with 2 MPPT controllers. Each MPPT controller can operate at its maximum power point without being affected by differences in voltage and current. No limitations caused by the weakest panels. You can add similar panels to each controller later on. Each controller manages an optimized input, avoiding energy imbalances. For more information, check the description of this video.